In this video, we will be discussing the 2024 February-March Paper 2. So before I proceed, I would like to give a disclaimer. So disclaimer, this question paper is not owned by the channel and the owner, and answer discussed in this question paper is not the marking scheme. And it's not by Cambridge. Okay, so whatever answer I discuss is just the opinion of myself and is used for sharing and discussion purposes only. Now, let's dive into question number 1. So bismuth is an element in group 15 of the periodic table. Bismuth has metallic bonding. So group 15, they belong under the P block. All right. So P block normally for non-metal, but because bismuth is way below nitrogen and phosphorus, right, they tend to show metallic bonding. But anyway, they already tell you it has metallic bonding. So they want you to draw a label diagram to show metallic bonding. So what is metallic bonding? It is the electrostatic attraction between cations and C of the localized electron. 1 mark is awarded, so I'm pretty sure C of the localized electron you must label, and I did show negative, 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 all right? And the cation, I need to see a Bi with a positive charge. Now, group 5, then maybe it's, they will donate all 5 electrons. So I will assume that they will donate all 5, for the delocalized sea of electrons. Okay, so maybe in the actual marking scheme, right, 5 electrons, as in possibly 5, may not be needed. Maybe they just award if you just put a Bi plus. All right, it's not to say that it must be a plus 5. Not too sure, but for me, I will safely assume since you're in group 5, you'll donate all 5. Okay, so second, bismuth reduces water to form bismuth oxide. Bi2O3, a colorless gas that ignites with a squeaky pop sound form. So a squeaky pop sound form means it's a hydrogen gas. So what you can see here is your bismuth here, all right? It's from 0, all right, to positive 3. This is oxidized. Whereas your hydrogen is positive 1, it was reduced down to hydrogen gas. Okay, yeah. So number 2, Bi2O3 is a yellow insoluble solid that melts at 1090 Kelvin. The molten compound conducts electricity. Deduce the structure and the bonding and explain your answer. So 1090 Kelvin is actually quite high. Okay, so first we need to address the high melting point. So I said the high melting point is due to strong ionic bonding. Okay, strong ionic bonding between the ions. All right, I did say Bi3 plus and O2 minus in the giant ionic lattice because they wanted the structure. Structure is giant ionic lattice. Bonding is ionic bonding. All right. Second, molten conduct electricity. All right. So electrical conductivity in molten state is due to free moving ions. If this is a metal, it is due to free moving electrons. So make sure you use the correct term. Free moving ions is for ionic compound. Free moving electrons is for metallic compounds. Okay, C. So Bi2O3 can be used to form the NaBiO3 shown in equation 1. So deduce the oxidation number in the bismuth in both compounds. So when you look at the NaBiO3, right, Na is group 1, so it's positive. That means the BiO3 is negative. It's just like CO3 2 minus. Okay, so if you want to calculate the bismuth oxidation number in BiO3, can you see the working on the right hand side here? So we put X as the oxidation number of bismuth. You got 3 oxygens, so it's 3 times -2. Total charge is -1, so X will be +5. All right. Now, the bismuth in the bismuth oxide is quite straightforward. It's +3. Now, please be reminded, oxidation number is symbol in front, number behind. Okay. Next, identify the reducing agent in equation 1. Okay. So the reducing agent means you oxidize another compound. Oh, sorry, you reduce other compound and you oxidize your own cell. All right. So you can see here, bismuth over here is +3 and over here is +5. So reducing agent means you oxidize your own self like this. So the reducing agent is the BiO3. So NaBiO3 is an oxidizing agent with similar properties to KMnO4. And figure 1.1 shows an example of the use of NaBiO3 as an oxidizing agent. Explain the term oxidizing agent. So oxidizing agent, I wrote, is a substance that oxidizes another compound and itself is being reduced, and I add on where oxidation number will decrease because you reduce your own self, so therefore your oxidation number will decrease. Maybe it's only the front part that is needed for the mark. Maybe the one oxidation number, maybe the mark is not allocated, but it's okay. I would like to write a little bit more elaborative. Okay. Now, part 2. Compound X forms when methylbutadiene reacts with KMnO4. State the essential conditions for this reaction. So what I did was, compound X given over here, look at the cursor, and I draw a methylbutadiene. So butadiene, 1, 2, 3, 4. Okay, so over here, maybe I label 1, 2, 3, 4. Number 2 got methyl. Okay, so what you realize is you open up the double bond to form a diol. So a diol requires a co-dilute acidified KMnO4 because the question just says KMnO4. So you need to write acidified. So complete table 1.1 to show what is observed when compound Y and Z react separately. Okay, now Y, maybe I just draw it here. Y is a ketone, okay, and your Z is an aldehyde, which is ethanol. Like this, all right? Now, sodium carbonate will not react with carbonyl compound, so it's no reaction for both. Alkaline iodine will detect for methyl ketone group, all right? So we can see that this is a methyl ketone group over here, all right? It will cut here, so this is a yellow PPT. Now, observation with Z, also yellow PPT, because ethanol is an exception for the triiodomethane test. Okay, so it will also show yellow PPT here. Now, 2,4-DNPH will detect both carbonyl compounds, so you can write orange PPT for both. And lastly, Tollens reagent is used to detect for aldehyde, so I'll put silver mirror for the compound Z. Okay, and no reaction for your propanol, which is Y. Construct an equation for the reaction of Z with NaBH4. So Z is ethanol over here. So I write CH3CHO. Aldehyde structural formula is CHO, not COH. OH is for alcohol, HO is for aldehyde. So you reduce aldehyde to primary alcohol. So what you can do in your working is you draw out the structure here, you draw out the structure there, okay? And then after that, you just go and write the structural formula, translate it back. Okay, so what you realize is you need to add 2 hydrogen at these 2. That's why you need to put 2 bracket H. Now, E, NaBiO3 can be used to determine the concentration of Mn2+. All right, our equation is shown in equation 2. Student uses the following procedure in the experiment. Add 100 cm³ of saturated Mn to a volumetric flask, and you make it into a diluted solution. So first, you add only 100. This is called 100. And then after that, you dilute it all the way up to 1,000 here. So this is 1,000 mark. All right, so there's a lot of water here and only very little of the saturated Mn2+. So you're doing a dilution over here. And you titrate 25. So you take out 25 here, all right, from the 1,000, and you do a titration. You just take 25 out, all right? And this 25 sample, okay, will be reacting with the NaBiO3, and they said 21.5 of 0.1 of NaBiO3 on top here. So therefore, over here is tighter 21.50 of the 0.1 of NaBiO3 was obtained. So calculate the concentration of Mn2+ in the saturated solution. Saturated means the red color pen, the original one, not the diluted one in the volumetric flask. Okay, so first we calculate the number of moles of NaBiO3. So 21.5 times 0.1 divided by 1,000 is 2.15 here. Now, according to the equation, okay, your NaBiO3 is 5. You want to find Mn2+ is 2. So you need to divide by 5 times 2. Therefore, this is the number of moles of Mn2+, but in a conical flask. All right. The Mn2 plus here is only the 25 centimeter cube in the conical flask. You need to find backwards to the volumetric flask, which is 1000. So in 1000 centimeter cube over here, all right? So what is the number of mole? If 25 centimeter cube is 8.6, 1000 centimeter cube is 0.0344. So the whole volumetric flask, the number of mole is 0.0344. Okay, now concentration therefore will be 0.0344 mole in 1 dm cube. 1000 centimeter cube is 1 dm cube. So hence this is my concentration. But this concentration is still in the 1000 centimeter cube or 1 dm cube. They want us to calculate the concentration of the saturated, which is the red color one, the down here. Okay, so dilution is M1V1 equal to M2V2. So the concentrated one is M1. I do not know what is the molarity of the concentrated one. And I took 100 of the concentrated one. And I diluted it into a 1000 centimeter cube volumetric flask with a final concentration of 0.0344. So hence you can find the saturated concentration as 0.344. Okay, yeah. So therefore you can pause the video and then after that you can write down. I will just proceed. Now next, question number 2. Chlorine reacts with many elements and compounds to form chloride. Table 2.1 shows information about some chlorides of period 3. So the formula of chloride for NaCl, all right, given Ne, I write NaCl, magnesium, MgCl2, and silicon as ICl4. So Na and magnesium, they are giant in terms of their chloride. SiCl4 is a simple molecular structure. Bonding, ionic, given covalent from the question paper. Now, what is the pH of NaCl? Neutral. Okay, neutral. NaCl is table salt, is neutral. NaOH is alkaline, that's called 13-14. NaCl is 7. MgCl2 is slightly acidic, 6.2. All right, anywhere from 6 to 7, but anyhow, they give it to us. Now, silica tetrachloride, they will hydrolyze in water and you give a acidic HCl solution. That's why it's anywhere from 1 to 4. I'll put a 2 because HCl is quite strong. Okay, now next. When Cl2 reacts with co-NaOH, Cl2 is both oxidized and reduced. The products are NaCl and G. State the type of redox in which the same species is both oxidized and reduced. So it's called disproportionation. Please make sure your spelling is correct. What is G? This one is memorization work, all right? Your G is NaClO. NaClO3 is for hot concentrated, which is the subsequent question. Write an equation for chlorine and hot. So they ask cold, they also ask hot. Okay, so this is also a memorization work. You need to memorize this. It's also a disproportionation reaction. Cold dilute NaOH and hot concentrated NaOH both are disproportionation with chlorine. Okay. Number 4, describe fully what is observed when silver nitrate is added to the aqueous solution of the chloride of sodium, followed by ammonia aqueous. So when you add NaCl with AgNO3, you will get a white PPT of silver chloride form, and then it will be soluble in dilute ammonia, okay, which is quite straightforward now, following your practical paper. Now, C, an excess of chlorine react with phosphorus to form PCl5. PCl5 is a simple molecule in gas phase. It also exists in solid in 2 other forms, which is given the 2 formula here. Complete the table 2.2 to identify the shape. Okay, now PCl5, there's 5. So if you look at phosphorus, right, they got 5 valence electrons here, right? So they will form with 5 chlorine. Okay, so over here, this one is a trigonal bipyramidal because it has 5 bond pair. Okay, 5 bond pair means trigonal bipyramidal. Now, PCl4 plus is tetrahedral, the given, it's okay. PCl6 minus is octahedral. Okay, why octahedral? Well, because PCl5, right? Okay, basically you find you already bond with 5 chlorine. Okay, so this is trigonal bipyramidal, 5 bond pair, 0 lone pair. Now PCl6, right? It means that you receive chloride here minus. Okay, chlorine is group 17. Okay, so you got 7 valence electrons, 1, 2, 3, 4, 5, 6, 7, and you receive an electron here. So the lone pair here will be donated into the phosphorus, right? So a neutral PCl5 and a Cl minus will give you PCl6 minus. So therefore, if after drawing this coordinate bond in, how many bond pairs are there for phosphorus with 6 chlorine and negative charge? You got 6 bond pair. 1, 2, 3, 4, 5, 6. 6 bond pair means octahedral. Okay, yeah. Now, part 2. PCl5 reacts with J to form H3PO4. Okay, identify J. So this one also memorization work. PCl5 will give H3PO4. So you reacted with H2O, and this is called hydrolysis. Okay, you only learn hydrolysis on the chloride of period 3. Okay, now, so just to add on, all right, make sure you know the other one. PCl3 also can undergo hydrolysis to give H3PO3. So you can see the number of chlorine is lesser, the number of oxygen is lesser. The number of chlorine is more, the number of oxygen is also more subsequently, accordingly as well. Okay. Now, donkey, chlorine reacts readily with propene. Okay, so chlorine reacting with propene here to form K, 1,2-dichloropropane. So complete the figure 2.2 to show the mechanism of the chlorine with propene in reaction 1. So you can see, all right, pause the video and check your answers. This is the electrophilic addition mechanism. Make sure your arrow is always pointing from either A, a bond, B, a lone pair. So you can see this arrow is pointing from a bond. This arrow also pointing from a bond, from. Whereas this arrow is pointing from a lone pair. Your arrow must come from either a bond or a lone pair. When you attack, of course, you attack an atom. So you point directly to your alphabet, your atom. Okay. Now over here, right, there's two possibilities, major and minor product. Okay, I mean major and minor intermediate. Sorry, let me change up. Major and minor intermediate. So because you're adding Cl, right? So eventually you only have one product. This is the only product that will form. Okay, but in terms of intermediate, right? Okay, some of you will put the carbocation ion, which is the positive charge, on the left carbon, and you will put the chlorine here, the first chlorine here. Okay, so this is different. The blue and the orange pen is different. Now, the reason why I draw the blue color pen version is because the blue color pen version, this one can give me a secondary carbocation ion. Okay, this version, this intermediate is secondary carbocation ion. Whereas the other intermediate that also can be formed, all right, this is a primary carbocation ion. Okay, now, so I would rather draw a more stable secondary carbocation ion rather than a less stable primary carbocation ion, even though both are able to give the same final product. Okay, so that would be my personal opinion. Now, identify the reagent and condition required for reaction 2. So let's look at reaction 2. Reaction 2, you remove, if you draw the whole thing out, every carbon must have 4 bonds, you remove HCl. So this is called elimination, NaOH ethanolic reflux, heat under reflux. Draw one repeat unit of the addition polymer that forms L. Okay, so this is your L. You want to draw the addition polymer, right? You need to focus on the double bond. Oops, let me just erase this. Okay, so you want to put the double bond in the middle, the bridge between the two vertical lines. Therefore, you will get your, I zoom out for you to see the whole thing. Can you see how the way I draw it? Can you see over here, the chlorine is here, the chlorine is here, the CH3 is here, the CH3 is here. Then these two, the hydrogen are hidden. All right, so that is the repeating unit. Okay, put the double bond in the middle. Then, of course, you have to extend the left and the right line over here. The extend the left, extend the right, extension bond. Okay, that will be the repeating unit. Question number 3. Nitrogen is generally an unreactive molecule, but it does react under certain conditions. Give 2 reasons to explain the lack of reactivity of nitrogen. Syllabus must know. Number 1, they have strong triple covalent bond between the 2 nitrogen atoms, very specific, not between molecules, between 2 nitrogen atoms. Number 2, it is a non-polar molecule. So when you're non-polar, you will not be easily attracted with any other molecule. All right, so nobody will want to react with you in general. And even if they want to, you have a strong triple covalent bond to, be broken, which is not easy. B, nitrogen can react with oxygen in an internal combustion engine to form a mixture of NO and NO2. Figure 3.1 shows a reaction scheme involving N2. Okay, so now write an equation to show the formation of a mixture of NO and NO2 in reaction 1. So nitrogen and oxygen to form NO and NO2, right? The balance equation is this. Okay, now give the formula of the product of reaction 2. So reaction 2, NO2 and H2O, they will form HNO3. Okay, of the products. Suddenly I'm like, S means maybe there's more than one. Let me just try. NO2 plus H2O to give HNO3. Okay. Let me try. I would like to add another one. You see, because I kind of last minute, but got S, that means plural. So that means maybe there's more than one. Okay. Now then after that, I tried to balance the equation and I realized that HNO3 is not the only product. Because if you only put HNO3, right, you wouldn't be able to balance the equation. Okay. Unless you introduce another HNO2, then only the equation can be balanced off. I mean, you can try, but I don't think you're able to balance the equation if HNO3 is your sole product. Okay, so I would like to change my answer, HNO3 and HNO2, given the last minute plural products. Number 3, state 1 environmental consequences of reaction 3. So reaction 3, must know your nitrogen dioxide and unburned hydrocarbon from your car, they will give you photochemical smog, and peroxide acetyl nitrate, PAN, is just one of the components of your photochemical smog. PAN is just one of the components. Okay, photochemical was a big thing. PAN is just one of the components inside the photochemical smog. Okay, now next. Haber process involves the reaction of nitrogen and hydrogen to form ammonia. Okay, so a catalyst is used which allows the process to be carried out at a lower temperature and pressure. Use the information in C to complete table 3.1. Okay, this one, right? I'm like, I start thinking for some time, but eventually, okay, I have to ask myself, enthalpy change of formation is defined as the energy change or enthalpy change when 1 mole of nitrogen is being formed or 1 mole of hydrogen is being formed, so on and so forth. So I ask myself the question here. When I constructed the cycle, you form the nitrogen here. You form from nitrogen in its standard states, under standard condition. Nitrogen is already N2G, and you still want to form an N2G. So what is the enthalpy change? 0. It's called you just take it from the air now. Okay, right? And then I ask myself, well, you want to form hydrogen, and hydrogen is already now at standard condition, H2 gaseous form. So you just need to go and take it from the air. Is there energy change? No, it's still 0. Okay, so the first 2 is 0. Now the last one may be a bit tricky. Okay, can be a bit tricky because if you see how I construct the cycle, right? The forward reaction here, okay, which is 92. Okay, and if you know formation-based cycle, that means if all the information given are formation data, like in this case here, you can use the formula product minus reactant. So who's your product? Your product is NH3, right? Okay, so NH3 is the arrow. This is the question mark that I need to find. Okay, this is the question mark I need to find. This one is the one that I'm going to look for. So the NH3 product is the one that I'm going to find. But I know that the enthalpy shift of the reaction, which is 92, 92 equals to product minus reactant. Both my reactant, okay, are 0. Okay, both my reactant here to form them are 0. So hence, what is your product? Your product is minus 92. Sometimes, if your cycle is not constructed correctly, or maybe if your direct and indirect is not very confident or strong, right, you may come up with a positive 92. Okay, so that are some of the careless mistakes that I can foresee here. So actually it's minus 92. Okay, yeah. Because if you want to prove back this 92, if you want to prove back, right? So let's say enthalpy of a reaction, ask you to calculate now. Given you these three numbers, you go and prove back. I give you these three numbers, 0, 0, and minus 92 in the table. Please go and calculate the enthalpy change of Haber process. You will take product, which is minus 92, product minus reactant. Hence, therefore, can prove up to minus 92. Okay? Explain how the presence of catalyst affects the reaction. Oh, the question is affect the reaction. Quite general, right? So I say catalyst does not affect the composition. I was a bit, careful. What kind of reaction? Too general. So I'm like, okay, in terms of composition base, I don't think catalyst will alter the composition. Composition means the amount. Okay, putting catalyst will not change the amount, but it will affect the rate of the reaction. So which part of the reaction you want me to discuss? So because you just say reaction, so I'm like, okay, I'm going to give you a composition version. I'm going to give you a rate version. So yes, a catalyst will speed up the rate of the reaction by lowering the activation energy of an alternative pathway. So the more molecules have greater energy than the activation energy, which is the EAC. After introducing the catalyst, it's called EAC. Okay, hence rate of reaction increases. No harm going a little bit more detail, because end of the day, you don't know where they want to allocate the marks. All right. Now, part 3. State and explain the effect, if any, on the rate. This time they bolded the rate on Haber process. So the rate pressure is lowered. So when pressure is lowered, the rate will decrease. I just answer straight to the point. When pressure is lowered, rate is decreasing, but that will only be one mark. But where is the second mark? So maybe I just explain a little bit more. I say because there's lesser frequency of collision between the molecules, hence lesser successful collision occur. Okay, when the frequency of collision decreases, right, the chances for successive collision will also decreases, hence your rate will decrease. Okay. Now, donkey. The N2F2 molecule has a double covalent bond between its nitrogen atom. Already tell you it's double between two nitrogen atoms. This consists of sigma and pi. Complete the figure 3.2 to show the dot and cross. So please look at the cursor here. Can you see the nitrogen on the left is X and the nitrogen on the right is dotted? Okay, so can you see that there's double bond here between the two nitrogen? So if nitrogen is group 5 and nitrogen is group 5, right, then the rest you can fill in the blank. Please make sure your lone pair, especially at the fluorine, the 3 lone pair, must show. Okay, don't forget your lone pair on the edges. Deduce the hybridization of nitrogen in N2F2. So nitrogen, okay, the structure, can you see I draw over here? Okay, nitrogen, if you focus, it has 3 electron cloud, 1 here, 2 here, and 3 here. So when you have 3 electron cloud, it's something like your ethene molecule, correct or not? You learn, right? Ethene is sp2, 1 electron cloud, 2 electron cloud, 3 electron cloud, right? So it's sp2. All right, so it follows your alkene. You apply accordingly, sp2. Now, make sure sp small, 2 must be on top. It's called superscript. Okay, cannot sp2 like this. No, this is not permissible. Okay, it has to be sp2 like this. Okay, now draw a diagram of the pi bond between the nitrogen atom. So not between nitrogen and fluorine, between nitrogen atoms. So you can see I put here N, I put here N. So pi bond is sideways overlapping of the 2p orbital of the 2 nitrogen atoms. So I draw my p orbital and I overlap it this way. If you want to draw the overlap sideways like this, like this, yes, they do. this is also accepted lah. Okay, can. But for me, normally I will just do this. It's easier. Okay. Now, question number 4. Compound S is used in food flavoring. A possible synthesis of S is shown in figure 4.1. So you pause the video, you take a look at yourself. All right, and I'm gonna answer part A. So P, Q, R, and S show stereoisomerism. Complete table 4.1 by identifying with a tick the type of stereoisomerism that each molecule shows. Okay, so let's look at P here. P will show geometrical isomers. All right, and the structure of P drawn here is the trans version. Okay, so it's just that they never draw the cis, they draw the trans version. Now, Q, I draw already after putting HBr. This is my Q here. You can see there's a chiral carbon. All right, so therefore, optical isomer, they tick for you. Then, halogen alkane can react with KCN in ethanol. Then you form your nitrile. That one also have a chiral carbon, so optical isomerism. H plus means acidic hydrolysis, AQ, hydrolysis in acidic condition. Then you give carboxylic acid. That one also has a chiral carbon. I put a star there, optical isomerism. Give the structural formula of Q. Okay, so let's just zoom out a little bit. Now, Q, can you see the drawing on top here? Okay, so I just spell out CH3, CH2, CHBr, and CH3. This is called structural formula. The spelling, only alphabet. Okay. Name the mechanism in reaction 2. So halogen alkane is reaction 2, sorry. I thought reaction 1. Name the mechanism in reaction 2. This is called nucleophilic substitution. Yeah, nucleophilic substitution. Reaction 2. Now, complete the equation for reaction 3. R is represented as C4H9CN. Okay, let me just zoom a bit more. Now, if you look at your R, okay, this is your R here. No, your R, for me, I like to write structural formula, but since they started off in a C4H9CN format, right? Okay, so what I do in general, I normally do this. I know that this leg is the one that is changing. You're changing from this leg to this leg. So that means this is status quo, this is status quo. And the one that I cancel off is the status quo, which is called C4H9. Okay, C4H9. So since it's status quo, I don't bother. I only look at CN converting to COOH. So I just need to look at the left and the right to compare. Okay, this C is this C. So therefore, you need 2 oxygen here, right? So therefore, I need 2 water molecule. All right. Then after that, you got 4 hydrogen here. Okay, and you got 1 here. You need another 3 more, right? But then your nitrogen, when you hydrolyze your nitrile, right, nitrogen will come out in ammonium, all right, NH4 plus. Okay, so the nitrogen in acidic condition will come out as NH4 plus, memorize. Alkaline will come out NH3, acidic will come out NH4 plus. So because there's a plus here, right, you need a acid H plus here to balance the charge. On the left got 1 positive, on the right got 1 positive. So if you count the total hydrogen on the left, don't look at the C4H9. You just count the hydrogen on the left, right? Here got 4, here got 1. Total is 5 on the left. On the right hand side, here got 1, here got 4. Total is also 5. Okay, so I tend to simplify my view to not look at the C4H9. I don't want to count too many things. Okay. Now, compounds, question C here. Compound S and T to form organic compound U, which has a single functional group. So you look at S, I put all the C in, all right, plus T to give U, all right. H2O come out. H2O come out means condensation. A small molecule coming out means condensation. So use the data of given in table 4.2 to show that U contains 7 carbon. The formula, hope you memorize it, 100 divided by 1.1 times the abundance of M plus 1 divided by the abundance of M plus. So you put this number here, you put the number bottom here. So you calculate 6.9, which is close to 7. So we prove that it is 7. So that's why I put here 7 carbon. U is 7 carbon. Okay. Now, then figure 4.2 shows the infrared spectrum of U. So where is U? Your 7 carbon here. Okay. This is the infrared spectrum here. right? I circle all the signal I've been reading here. Now you can pause the video, or you can open another tab for to look at the data booklet from 2022 to 2024. All right, they have the 2022-2024 data booklet in your syllabus, but in exam they won't give it to you. They'll give it in a question paper like this. Okay, but if you want to look parallelly or side by side screen, all right, you can open another tab to look at this table. Okay, so to answer the question, okay, based on these three signal here, right, I know it's an ester. Okay, I know it's an ester. So for me, it's the function group of U is an ester. That means the 7 carbon, all right, the product is an ester. Explanation, I just say because there's 3 signal and I code out everything. I code out the 3 signal that I circled just now. Now, when you code out the signal, right, you may give the range like this. I just copy the whole range, okay? And please copy word for word. CH alkane, I just copy the whole thing out, okay? Now, please do not show the line. So a lot of students, this particular column here, they just write OH, they just write NH, they just write CH. No, please show C-H. The bond must be shown because infrared will cause the bond to vibrate. So we want to know which covalent bond that's vibrating. So you have to show the bond. All right. So I did show the bond here. I did show the double bond here. I did show the single bond here. Okay, so you may write a range, you may write a specific number. Now, my C double bond O, right, 1740, because this is a number that I speculated out. So this 1005, 1006, 1007, so it's before the half, right? So I just speculate 1740. You can put a number 1740. If not, you want, you can quote out the whole thing, 1710 to 1750. You want, you can. So you change. If you don't want this version, you can put this here. All right. And then the last one, C single bond O, 1280. I speculate out. If you're not confident, then you just go and put the whole range, this one, copy in your text. Okay. Yeah. So this one is an ester. Now, so let's look at T. Where is T? T. Okay. Now, U has 7 carbon. I count S now. 1, 2, 3, 4, 5. There's 5 carbon in S. So that means your T, the other reactant, has 2 carbon. 5 plus 2 will give 7. So for T, right, T has a single functional group. All right. Draw the structure of T and U. So this is reactant on the left. And this is the ester product on the right that has 7 carbon. Correct? So since they already gave me the S is here all the way until here. This is S, right? This is S. Okay. Therefore, you know carboxylic acid, you need alcohol, right? So your alcohol must be 2 carbon length. So this is ethanol. So this is my ethanol, and this is my ethyl ester. Okay, wow. We can't IUPAC or so-called systematic nomenclature, right? Can. Come. Ethyl. Okay. Now the main chain would be here. This would be the main chain. Okay, 1, 2, 3, 4. So ethyl, all right. Then our bracket now. 2-methyl butanoate. Because this is 1, this is 2, this is 3, this is 4 on the butanoic acid. So number 2, there's a methyl. So 2-methyl butanoate. Ethyl 2-methyl butanoate. So this will be my ester name now. Okay, I don't think this one will be asked at A level, all right, because you have a branch on your ester. Unlikely they'll ask you. All right. Now another thing I want to comment is draw the structures. Okay. So as you can see, I purposely draw 2 different structures for you to see. On the left one is called a display formula. On the right one, no specification. All right. It's basically a merging of structural and display. So when they say draw structure, right, you actually can draw anything you want. Okay. Unless they explicitly stated in the question, draw display formula. Then all the bonds must be shown, which is like the T. Okay, and but normally they don't lah. 9 out of 10 times they don't really control your drawing in what kind of formula. Okay, yeah. So I purposely draw two different things just to let you all know that any formula of drawing is accepted. Okay, and if you have any question, you just leave a comment and I will get back to you.